Chapter 5, Stereochemistry. Stereochemistry is a subject that comes from the category of isomerism. So to better understand what stereochemistry is about, it's also important to understand isomerism phenomena. What is isomerism? This term always refers to molecules that have the same molecular formula but differ in the arrangement of their atoms. And that's why we call them isomers. We heard the term structural isomers or constitutional isomers previously. That's one type of isomerism. So there are two main types of isomerism. One that is structural isomerism, and the second is stereoisomerism. Both of them are defined to have molecules that share the same molecular formula. But the one that is labeled structural or constitutional isomerism, that usually refers to compounds with different connections between atoms. And we will see examples of those, structural isomers or constitutional isomers. The ones that we put them under the label of stereoisomerism, these are compounds with same connections between atoms, but their atoms are arranged differently in space. And we will see examples of those as well. So we could see the key word in structural isomerism is the different connectivity, and the key word in stereoisomerism is the same connectivity but different arrangement in space. Keep that in mind. So let's talk about the first type of isomerism, constitutional isomerism, which we just defined as basically compounds that have the same chemical formula, but the atoms are connected in a different order. And here's some examples of that. So you have the compounds on the left, it's a C4H10. Compounds on the right, it's also C4H10. But you could see clearly that this is butane, while this one is 2-methylpropane. What are these two structures? Since they have the same chemical formula, but different connectivity, that makes them a pair of constitutional isomers. Here's another example. I could have functional groups in there. Here's an alcohol. So I could see here 3 carbons in the chain with an OH at the end. Here's I see 3 carbons in the chain with the OH in the center. Are these two structures the same exact molecule? No. This molecule has a hydroxy group at the terminal. This compound has a hydroxyl group on the center of the molecule. So these two would be basically a pair of, again, constitutional isomers or structural isomers. Here's another. Do these two structures that are constitutional or structural have to be the same functional group? No. The answer is no to that question. Here's a compound. They have 2 carbons with 6 hydrogens and oxygen. Here's 2 carbons with 6 hydrogens and an oxygen. This compound is an alcohol. This compound is an ether. That makes those two structures have different connectivity even though they have the same chemical formula. Therefore, they are basically considered constitutional isomers. Here's another one. You can see clearly that I have an alkene on the left, and I have a cyclic alkene on the right. Both structures have the same number of atoms, have different connectivity, and that's what makes them a pair of structural isomers. So whether you use constitutional or the word structural means the same thing, that these two compounds usually are compounds that have the same chemical formula but different connectivity. So that's the first type of isomerism. The second type of isomerism, which we defined as compounds with atoms bonded in the same order, same connectivity, but their atoms have different orientation in space. And here, when we say different orientation in space, right away we have to acknowledge that there are 2 subtypes of stereoisomerism. One of those subtypes you have heard already in a previous chapter. So the first subtype is optical isomerism, and the second subtype is geometrical isomerism. Both types of isomerism, which are stereoisomerism, have the same connectivity, but the different arrangement in space kind of be different when we look at these two types of stereoisomerism. The first one, which is optical isomerism, these are basically compounds that have opposite effect on plane polarized light. It's a term we use in a machine that we use that's called polarimeter. We will see it today. And this polarimeter goes after the activity of the compound, how it rotates this plane polarized light. And it gives it basically a value. And we will talk more about that. But any pair of compounds that are different from each other in that effect on plane polarized light, we will basically label those two compounds as optical isomers, as long as these two compounds are the same in terms of connectivity. So same chemical formula, same connectivity, different effect on plane polarized light, and not just different, opposite to each other. The second type of stereoisomerism is geometrical isomerism. What is that about? It has to do with cis and trans. Occurs when atoms or groups of atoms assume different positions around a rigid ring or a bond. And that bond usually is a double bond. We've seen this term previously, and we know that alkene structures or cyclic alkanes, these are the two type of compounds that we can use cis and trans isomerism in them. And that's where we would find geometric isomerism. So here's a chart that we can actually pause for a second and ask ourselves. If I'm asked to identify the relationship between two molecules, the first question I would ask, do they have the same molecular formula? If the answer is no, then they cannot be isomers. Regardless what type of isomerism it is, if the two compounds don't have the same chemical formula, right away, they cannot be isomers of each other. But if the answer is yes, then there is a possibility for those two compounds to be isomers. But what type of isomerism? Are we talking constitutional, or are we saying stereoisomerism? We're going to have to ask the question, do they have the same connectivity? If the answer is no, then we are dealing with two constitutional isomers. But if the answer is yes, they have the same connectivity, then we're going to ask the question, are they the same exact molecule? If the answer is yes, then they are the same. But if the answer is no, that they have the same connectivity, but they are not the same, that means they are stereoisomers of each other. And that's where I need to keep in mind that I have two types of stereoisomerism. Are they optical stereoisomers, or are they geometrical stereoisomers? Geometrical stereoisomers, these are the cis and trans, alkenes or cyclic alkanes. Optical isomers, these are the compounds that usually are different in rotating the plane polarized light when we inject them in a polarimeter. So optical isomerism. Those compounds that have to do with plane polarized light, what do they all have? They all have a chiral center. What's a chiral center? It's an atom bonded to 4 different atoms or groups of atoms. And here's an example. I can have the one on the left. I could see here that I have a carbon attached to an oxygen, attached to a hydrogen, attached to another carbon, and attached to a 4th group that is a carboxylic acid. So I could view the 4 groups that are connected to this carbon, and I can see clearly that these 4 are different atoms or groups of atoms. And that's what makes this carbon in the center a chiral center. Does the molecule have the ability to have more than one chiral center? The answer is yes. Here's another example. You can see here the carbon on top has a nitrogen, a hydrogen, a carbon that's different from the other carbon. So that's a chiral center. Look at the carbon at the bottom. See here, they have an oxygen, hydrogen, carbon that's different from the other carbon. So somebody would say, okay, well, you just say different atoms or groups of atoms. Yes, these two have the same atom, but these two don't have the same group. This is a group of amino acid. This is a group of methyl. So that's why this carbon will also be considered a chiral center. Chiral isomers that are non-superimposable, and this is a term you're probably hearing it for the first time. Non-superimposable mirror images of each other are usually enantiomers. Think of your two hands. Your both hands, when you put them in front of each other, they are technically mirror image of each other. And when I say non-superimposable, if you would put one hand on top of the other, you're gonna find that the two thumbs, they're not the same. They are directing toward different sides. That's what we mean by non-superimposable. So when I look at these molecules, and I see here that I have an alcohol on the right, I have a methyl on the left, and I have a carboxylic acid on top. And let's assume there is a mirror. And the mirror in front of the molecule will show this second one in the mirror, having the OH facing it, having the CH3 facing away. This would be a mirror image of the first. And not just that, if you take these molecules and you put it on top of the first, they're not going to be superimposable. They're going to be non-superimposable. And these are the two criteria that usually exist in optical isomers that are enantiomers. There are other types of optical isomers. The very first type we're going to learn is enantiomers. What are enantiomers? Molecules that have same chemical formula, same connectivity, different arrangement in space, rotating the plane polarized light in opposite direction. And not just that, they are mirror image of each other, non-superimposable. So once again, enantiomers, they are optical isomers. And these optical isomers, they don't just differ in rotating the plane polarized light opposite to each other, but they also are mirror image of each other, non-superimposable, just like your two hands. Just keep that in mind. Can I have a structure that has more than one chiral center, enantiomer of another? Yes. Here's an example. You could see here, this carbon has an NH2 to the right, a hydrogen to the left. If you put a mirror, and you will see that the other structure, it's actually a mirror image of the first. So this part is the mirror image of this part, and the bottom part has the OH to the right. The bottom part in the second molecule has the OH on the left. So you could see clearly the entire molecule is a mirror image of the second. And not just that, it's a non-superimposable. Take this molecule and put it on top of the first. They're not going to be superimposable. They will be non-superimposable. So that's important to keep in mind, that the two criteria have to be fulfilled before I label a pair that they are a pair of enantiomers. This is the polarimeter that we were talking about, where the plane polarized light being checked. So we inject the sample, and if the sample has a chiral center that has the ability to rotate the plane polarized light, is going to rotate it in a certain degree. We will expect the enantiomer to rotate the plane polarized light with the same degree, but in the opposite direction. So there are a couple terms that we're going to need to keep in mind when it has to do with the polarimeter. Dextrorotatory is when the plane polarized light rotates to the right, so positive. So dextro means right. Levorotatory, which means the plane polarized light being rotated to the left. So when I say D in front of a molecule name, that means I'm talking about the plane polarized light being rotated to the right when it's injected in a polarimeter. When I have a letter L in front of the compound and it says minus or an L only, either of the two, minus or L, will mean that the plane polarized light got rotated to the left when this sample was injected in a polarimeter. So that's important to keep in mind. Dextrorotatory or plus, clockwise, levorotatory or minus, counterclockwise. A mixture of enantiomers in equal proportions is optically inactive. Think about it. If I have a molecule, and I want to check the polarity of it. I look at the bonds within the molecule. If I see the dipole moment going to the right is being canceled with a dipole moment going to the left, the molecule, even though it does have polar bonds, the molecule overall will be nonpolar. Same thing is applied here. If I have two compounds in a sample, and these two compounds are enantiomers, they are mirror image of each other, non-superimposable. That means one will rotate the light, the plane polarized light, to the right, and one is going to rotate the plane polarized light to the left. So the overall activity is zero. And that's why we would call them mixture like that optically inactive. And that's usually where the term racemic mixture exists. Racemic mixture is a mixture of enantiomers in 50-50%. 50-50%. What if there is one enantiomer in excess of the other? Of course, there will be optical activity then, because you don't have a 100% cancellation in terms of plane polarized light. So you have some going toward one over the other. And that's why that's another term we will talk about today, that is optical purity or excess enantiomeric. So that's, or enantiomeric excess percent. That's type of calculations we will be working on today. Back to the other type of stereoisomerism, which is geometric isomerism. This refers to two molecules that have the same chemical formula, same connectivity, but different arrangement in space. But what kind of arrangement? Cis and trans. And it's important to keep in mind when we look at an alkene that the two groups cross each carbon of that double bond should be different. So this methyl is going to be higher in priority than the hydrogen. Same thing here, the methyl is higher in priority than the other hydrogen. So we could see clearly that these two methyl groups are facing the same side, that's why it's a cis. If they are facing the opposite sides of each other, that would be a trans. Same thing applies if I would be dealing with a cycloalkane. This structure will have a cis isomerism or geometric isomerism. This would have a trans. If I would be dealing with an alkene where one side has the same group, you're going to ask yourself, all right, which one is going to have a higher priority? You're not going to have an answer for that. Therefore, in that case, you're not going to label the compound cis nor trans, because that will not have the eligibility to basically fulfill the cis and trans isomerism requirement. Same thing is applied here. So you could see here that the alkene on the left, you have a methyl and a methyl. So you could see here that the Cl on the opposite side of methyl, where the two methyls are actually facing the same side. This is same connectivity, but different arrangement in space. And that's what makes these two compounds now, they are not just non-mirror image of each other, they are also non-superimposable. So that's one thing to keep in mind. Every single cis and trans pair will always be non-mirror image of each other and non-superimposable. It's different from the term that we just seen earlier, enantiomers. Enantiomers, these are compounds that are mirror image of each other, and they are non-superimposable. Mirror image of each other and non-superimposable. While here, geometric isomerism involves the two compounds to be non-mirror image and non-superimposable. So here, just to remind you, molecules with more than one chiral center usually have mirror image stereoisomers that are enantiomers. What if I have a compound, say this one in the middle, and I look at the one on the left, I look at the carbon on top, I see it exactly the same. So these two carbons are not mirror image of each other, while the bottom carbon, if I look at the two carbons, they are mirror image of each other. Can I have a compound half mirror image, half non-superimposable, and still call it enantiomers? No, you cannot. What would the proper term be for these two compounds that are partially non-superimposable partially non-mirror image. So you can see here that this carbon is a mirror image of the second, but the top carbon is not. You could see that this carbon is non-superimposable, but this carbon is superimposable. What is the relationship between these two compounds now? They are diastereomers because they are non-mirror image of each other overall, and they are non-superimposable. So this term, diastereomers, is usually used for two types of compounds: cis and trans, because they are non-superimposable and non-mirror image, and they are also used for compounds that are not fully enantiomers. They are partially non-superimposable, partially mirror image. Therefore, they will be labeled diastereomers. Here's another example. You could take a look at the one on the right and compare it to the one in the center. Look at the top carbon. It's a mirror image, and it's non-superimposable of the same carbon on the second molecule, while the bottom carbon, you can see it clearly that it's the same exact of that carbon in the second molecule. So because of the fact that they have more than one chiral center, one is similar and one is not, that makes them basically non-mirror image of each other, non-superimposable, therefore they will be labeled diastereomers. So it's very important to keep in mind those two terms, enantiomers and diastereomers. What are enantiomers? Molecules that have opposite effect on plane polarized light. And they are mirror image of each other, non-superimposable. You can see me, I always use my hands as an example of those enantiomers. Diastereomers, these are compounds that have more than one chiral center, and they may have one that is the same, but one that is opposite, meaning mirror image, non-superimposable. So the fact that they are partially non-superimposable, partially mirror image, these pairs will be referred to as diastereomers. Where else can I use the term diastereomers? Cis and trans alkenes, cis and trans cyclic alkenes. So that's an important thing to keep in mind. So here is the chart one more time, just to remind you of what we discussed today so far. If I'm asked to label two compounds, what's the relationship between them? I ask myself, do they have the same molecular formula? If the answer is no, they are not isomers. If the answer is yes, they are isomers. The next question would be, what kind of isomerism do they have? Well, ask yourself, do they have the same connectivity? If the answer is no, then they are constitutional isomers. If the answer is yes, they are. Now, are they exactly the same? If they are exactly the same, then they are the same exact molecule. But if they don't have, if they have the same connectivity, but they are different arrangement in space, then they are stereoisomers of each other. The next question would be, are they mirror image of each other? Because if they are mirror image of each other, then they are enantiomers. If they are not mirror image of each other, then they are diastereomers. Cis and trans isomerism could also exist in non-organic molecules, like in the metal complex that you see in front of you. It's a platinum ammonia chloride complex. You can see here the one on the left is a cis, the one on the right is trans. It's interesting that this molecule shows biological activity when it's in the cis form, and it shows no biological activity when it's in the trans form. So this molecule on the left, which is the cisplatin, is an anti-tumor agent and it's still used today. So you can see clearly here an example of molecules that have biological activity depending on stereochemistry of the molecule. So the configuration or the arrangement of atoms in the molecule, it does affect biological activity. And that's where the billions of dollars invested in the drug industry, they always have to consider the stereochemistry aspect in the molecule, thinking how would it bind the biological active site in the human, or how it would bind to the enzyme, or whatever it is the case. I need to keep those groups in the molecule in a certain orientation to fit the bucket that's going to actually attach to release the biological activity. So that's an important aspect that we have to always keep in mind, the stereochemistry of the compound. Here's another term that we have to be familiar with, chiral or achiral. We just learned what chiral compound means. Chiral compounds, those are the ones that have a chiral center. And what's a chiral center? An atom that has 4 different atoms or groups of atoms. And just to remind you, these are the 2 molecules that we used earlier. You could see here that the carbon in the center, it's a chiral center. And due to the existence of the chiral center, that makes the compound a chiral compound. If I have an example of a compound that I can see clearly that there is a plane of symmetry. What does plane of symmetry mean? If I draw a line, I could see clearly that if I draw a line crossing 1 and 4, carbon 1 and carbon 4 on the one on the left in the methyl cyclohexane, you could see clearly that the right-hand side molecule, half of the molecule, is the same exact as the left-hand side of the molecule. That makes this compound have achirality, means the plane of symmetry will always make the compound an achiral compound. How would that achiral phenomena be reversed to make it a chiral? I will place a group on either side of that molecule to make the plane of symmetry invalid. Invalid, meaning the one on the right, the right-hand side, cannot be the same exact half on the left-hand side. So the one on the right, you could see clearly now, if I look at carbon number 2, what do I have? I have a methyl, I have a hydrogen, I have a CH2, and I have a carbonyl. 4 different groups that makes this carbon number 2 a chiral center. Therefore, the compound is a chiral compound. So it's important to keep in mind that every single time you see a molecule that has a plane of symmetry, dividing the molecule into 2 halves that are exactly the same, right away, that will be an example of an achiral compound. Achiral compound. Here's an interesting phenomenon, and that's the last thing we're going to talk about in this PowerPoint slide. Achiral always connected to 2 types of structures. One type that has no chiral centers, as we've seen here earlier, and another type of compounds that has a plane of symmetry, even though it does have chiral centers. Even though it does have a chiral center. What is that supposed to mean? Let's look at the examples at the bottom of this page. You could see here, carbon number 2, it's a mirror image, non-superimposable of the carbon number 2 in the second molecule. Carbon number 3, it's a mirror image, non-superimposable of carbon number 3 in the second. So you can see clearly that these 2 compounds are not just mirror image of each other, they are non-superimposable. So that makes those 2 this pair of enantiomers. Let's look at the one on the right. This pair right here. So we could see here carbon number 2, it's a mirror image non-superimposable. Carbon number 3, mirror image non-superimposable of carbon number 3 as well. However, we need to observe one thing here and highlight it. That is, there is a plane of symmetry that divides the molecule into 2 halves that are exactly the same. And because of that, even though I have a chiral center in the compound, that makes those 2 structures that they seem enantiomers to me, but because of the plane of symmetry, makes those 2 compounds achiral. And not just that, there is a term that we usually associate this phenomena with, meso compounds. Meso compounds usually, those are compounds that have chiral centers. Looking at the 2 compounds, you would think they are a pair of enantiomers, but because of the plane of symmetry, that makes the pair of enantiomers now meso compounds achiral, identical. Achiral, identical. That's very important to keep in mind. So now we know that we can use the achiral term, not just for compounds that have no chiral centers, but also for compounds that have 2 chiral centers or more, and they have a plane of symmetry that makes the enantiomer of it no longer an enantiomer due to the plane of symmetry existence. And that makes the pair of compounds that have a plane of symmetry, even though they have chiral centers, meso-identical achiral compounds. And that's the first part of chapter 5.